Hi everybody, Mr. Johnson here. Today we're going to talk about precision and accuracy in measurement making. As we've seen from our experiments in class, data from groups can vary quite a bit. To help minimize this, we're going to try and make the most accurate measurements we can, and so we're going to take a look at an example. Let's imagine that this represents a part of a meter stick and that the units are in centimeters. The arrow represents the length of the item that we are trying to measure. We can clearly see that the object is more than 6 centimeters and that it is in less than 7 centimeters. As we're also familiar, there are 10 marks in between the 6 and the 7, breaking it up into 1/10 of a centimeter. And so we can see that it is 1, 2, 3, 4, 5, 6, 7, 8. It is longer than 6.8 centimeters. That 6.8 centimeters has no uncertainty. Anybody could look at this meter stick and would come up with it being at least 6.8 centimeters long. But we can go a bit further. Let's imagine for a moment that we were able to divide this line into 10 further spots. Okay, so we're going to be looking right here. And let's imagine that we can split that a little bit more. So, hard to do on an iPad. All right, pretty lousy. But hopefully you get the idea. In most cases, you wouldn't be doing this on paper. You would kind of trying to imagine it. If we imagine that I drew these evenly spaced, we can sort of mentally project 10 additional spaces in it. And based on my lines here, it looks like it's the third one in. Now, these lines represent 1/10 of a centimeter. Dividing it 10 more times, each line in blue represents 0.01 centimeters. And we can go in 1, 2, 3. So that actually makes our would make the number 2.83 centimeters. Now, that's the number I got. That last measurement has a bit of uncertainty. Someone else could easily measure maybe 6.82, 6.84, but it's definitely not 6.85 because we can clearly see that that arrow is really not at the halfway point. So really 6.81 to 6.84 would probably be pretty reasonable for this. In the scientific community, it's always best to include every digit that we are certain about. That's the 6 and the 0.8. We can be absolutely certain about that. And one additional digit. That is the one we estimate. We always include that. It feels kind of wrong to include a digit that you're sort of estimating, but scientists around the world have agreed to include this single estimated digit so that we can tell that, well, it's not exactly 6 it's actually a little bit more. So all the digits in 6.83 are important, even the last one that is estimated. And we say that all the digits are significant. Now, what is a significant figure? So significant figures, those are, again, all the digits that we know for sure, plus one place that is estimated, and that is how we always want to record our measurements. And the uncertainty is going to be basically just based on our ability to estimate what that final digit is. And there are other things that can affect the uncertainty. For example, we had pretty widely spaced lines, so we could easily imagine 10 little lines further dividing it. But if you have something that's really, really narrow and it's hard to, you can't really imagine 10 lines in between it, you can do less than that. And we'll take a look at two quick examples. So here, the example on the left is, it's basically the same example. It's a little narrower. Some people might not be able to make 10 little dividing lines in between that. So what we can do is, instead, we can just pick a number that, that we feel comfortable with. So maybe 5, for example. And so we would say that this is, again, it's 6. We could be certain of that. 1, 2, 3, 4, 5, 6, 7, 8. And we're about 2 lines in. Now, the one thing you have to be careful of here is that that distance is 0.1 centimeters, and it's been divided up 5 times. So each of those lines is going to be 0.02 centimeters. Okay, so it's that difference here. That's 0.1 centimeter. There's 5 lines we drew, so just divide it. It's 0.02. It looks, if these were even, this looks like it's at about that second line. So we would put a 6.84 centimeters. Always important to include the units. Okay, this you could do this in the case that you didn't think you could get 10 lines drawn in there. If we look at if the lines are even further closer together, another thing we can do is you can do even less, right? If you wanted to, let's try this again. If you wanted to split it right down the middle, if the lines are really, really close together, this would allow us to say that it's, so we can see that it's 6.1, 2, 3, 4, 5, 6, 7, 8. And, well, that line here, that arrow looks like it's right on the midpoint, so we're just going to round to that nearest half. So, those are ways that you can measure using smaller scales. And again, just as a summary, all the digits that we included are significant. All of them are ones we're absolutely positive about, except for the last digit. That is estimated. So this absolutely takes some practice. So I've included a worksheet on reading scales. So just record your answers as accurately as possible, and be sure to include that final estimated digit. When you're done, you can. It has a column for counting how many digits you have, and that is just the significant figures. It's abbreviated with an SF, significant figures. In this example, we would for 6.84 we'd have 1, 2, 3 significant figures. That is something that's going to be important later and carry on into physics. So try these out and be sure to come in with questions tomorrow. Good luck.